Welcome to the continuation of the lecture on the non-radiating dielectric guide. So, in this part we are going to find out the explicit field expressions in the dielectric and air regions for the LSM and the LSE modes of the NRD, and thereafter we are going to move to the characteristic equations for the NRD, which is going to yield a complete set of equations for characterizing the NRD and its dispersion characteristics. So, in our previous lecture we had explicitly written down the potential functions for the LSM even and the LSM odd modes for the NRD in the air and dielectric regions. From these potential functions, as we said that we can use the expressions which relate the electric and magnetic fields with the psi function for this substitution. So, the electric and magnetic fields resulting out of this condition A equal to ux psi. So, they can be used to find out the electric and magnetic fields of the LSM modes, because this characterizes the LSM modes. As we said that there is no magnetic tangential, as we said that there is no normal component of the magnetic field to the air dielectric interface. So, it is a TM to X mode. So, therefore, this equation characterizes the LSM modes or LSM modes, and therefore, we have already derived the relationship between the psi function and the electric and magnetic fields for this mode, or we have expressed the electric and magnetic field in terms of the psi function for this kind of substitution before. So, we will use exactly those electric and magnetic fields resulting out of this condition of the magnetic vector potential, which characterizes the TM to X mode. So, we are not going to write those electric and magnetic field equations because we already know them. What we are going to use them in order to find out the electric and magnetic fields for the LSM even and LSM odd modes. Okay. So, I can just write for reference the electric field. So, Ex we found that as 1 by j omega epsilon del square del x square plus k square psi, and so on and so forth, and finally, if you go to Hz, it was found as minus del psi del y. So, you go through all those sets of equations for this condition which we derived before, and from those equations we can find out the explicit forms of the electric and magnetic fields for the LSM even and LSM odd modes. So, now we come to the potential functions for the LSE even modes. So, we are not going to explain too much here, we are just going to write it down for reference sake, because we are already now familiar with the LSM even and odd modes. So, in the dielectric region, which is mod x less than or equal to b by 2, we have psi equal to b dE cos q me prime x cos n pi y by b cos n pi y by a e to the power minus j k z e prime z. So, again this stands for the dielectric, this stands for the even mode, this is the odd variation sorry, this is the even variation, this is the even variation of the LSE for the LSE even mode. This again refers to the condition that the tangential electric field has to vanish on the metal plates, that is how this condition is chosen, and this refers to the longitudinal behavior along the, this refers to the variation, this refers to the variation of the potential function along the z direction. So, when there is propagation. So, this again refers to the even mode. So, similarly, in the air region, that is for mod x greater than or equal to b by 2, we have psi equal to b a e exponential minus p m e prime mod x minus b by 2 cos n pi y by a e to the power minus j k z e prime z. This prime denotes the LSE modes. Okay. So, this is pretty much similar. So, we say that this A refers to the air region, E refers to the even mode which is here, minus P m E prime refers to the eigen mode in the air region, the eigenvalue in the air region. This refers to the exponential decay of the fields in the air region, and these two terms we have already encountered previously. So, again if I write it now for the LSE odd mode, in the dielectric region, for mod x less than equal to b by 2, we have psi is equal to BDO, we have psi equal to BDO sin q m o prime x cos n pi y by a e power minus j k z o prime z. So, this is the odd mode. So, we have the sine here, this is the odd, and these two terms we have already encountered. In the air region, which is mod x greater than or equal to b by 2, we have psi equal to BAO exponential minus PMO prime mod x minus b by 2 cos of n pi y by a e to the power minus j k z not z e to the power minus j k z not prime z, that is for x greater than or equal to b by 2, and that is equal to minus B A O because it is the odd mode. Okay. So, minus BAO exponential minus PMO prime mod x minus b by 2 mod x minus b by 2 cos of n pi y by a e to the power minus j k z naught prime z, that is for x less than or equal to minus b by 2. And the reason why for the odd mode these are two different expressions is the same as the LSM odd mode. Okay. As to why these are two separate expressions, because it is the odd mode and we have to match the fields on both the regions. So, here QME prime, PME prime, QMO prime and PMO prime are the eigenvalues of the characteristic equation for the LSE even and odd modes. We have already seen that. The subscript E referring to the even mode and the subscript O referring to the odd mode, and these are the amplitude terms. So, these are the so these are the amplitude terms BDE, BAE, BDO and BAO. Now, from these potential functions, because the LSE mode is nothing but the TE to x mode, it is the TE to x mode because there is no electric field along or no electric field, because there is no electric field normal to the air dielectric interface. So, it is transverse electric to x. So, therefore, it can be obtained from the expression F equal to U x psi. The expressions for the electric and magnetic fields we obtained for this condition are exactly the same electric and magnetic fields we would obtain for both the LSE even and LSE odd modes, because they are TE to x modes. So, I do not need to write those equations explicitly because we have already covered those equations, but for reference's sake I will just write down the value of E x. So, E x was 0 and all the way down, if you had gone to H z, you would have met this expression 1 by j omega mu del square psi del x del z. We have already covered all these 6 sets of equations, and therefore, I will not write them down again. So, using these expressions, the explicit expressions for the electric and magnetic fields for all the modes can be written down. Okay. So, we can quickly write down the expressions for the modes. So, for the LSM even mode, in the dielectric region, which is mod x less than or equal to b by 2, we have E x equal to A d E k 0 square epsilon r minus q m e square. Please verify these expressions by j omega epsilon naught epsilon r cos q m e x sin n pi y by a e to the power minus j k z e z. Okay. So, as we said that these expressions are the one which are obtained from A is equal to u x psi, which we already wrote down before. This expression, okay. And these we are explicitly writing down by substituting psi here. Okay. So, please verify those expressions yourself. E y will be equal to minus A d E q m e n pi by a by j omega epsilon naught epsilon r sin q m e x cos n pi y by a e to the power minus j k z e z. E z is A d E k z e q m e by omega epsilon 0 epsilon r sin q m e x sin n pi y by a e to the power minus j k z e z. H x is 0, H y is given by minus A d E j k z e cos q m e x sin n pi y by b sin n pi y by a e to the power minus j k z e z, and H z is given by minus A d E n pi by a cos q m e x cos n pi y by a e to the power minus j k z e z. This completes the set of electric and magnetic fields in the dielectric region. Now, if you want to write down the fields in the air region, they can similarly be written by using the appropriate psi function for the air region. So, in the air region we have mod x greater than or equal to v by 2, we will have E x as AAE PME square plus K 0 square by j omega epsilon naught exponential minus PME mod x minus b by 2 sin n pi y by a e to the power minus j k z e z. E y is minus a e p m e n pi divided by j omega a epsilon naught exponential minus p m e mod x minus b by 2 cos n pi y by a e to the power minus j k z e z, that is for x greater than or equal to b by 2, and that is equal to AAE PME n pi by j omega a epsilon naught exponential minus PME mod x minus b by 2 cos of n pi y by a e to the power minus j k z e z, e to the power minus j k z e z, that is for x less than or equal to minus b by 2. So, the fields change in the two air regions, the fields change in the two air regions, region 1 and region 3. Okay. Similarly, we have E z as AAE KZE PME by omega epsilon naught exponential minus PME mod x minus b by 2 sin n pi y by a e to the power minus j k z e z, that is for x greater than or equal to b by 2 . And that is equal to minus AAE KZE PME by omega epsilon naught exponential minus P m E mod x minus b by 2 sin n pi y by a e to the power minus j k z e z for x less than or equal to minus b by 2. H x is 0, H y is minus a a e j k z e exponential minus p m e mod x minus b by 2 sin n pi y by a e to the power minus j k z e z, and h z is minus a e n pi by a exponential minus p m e mod x minus b by 2 cos n pi y by a e to the power minus j k z e z. Now, if we equate the tangential magnetic fields at the air dielectric interface, so equating the tangential magnetic fields at the air dielectric interface, we will get, please verify again this expression, AAE is equal to ADE cos QME B by 2. Okay. So, let us stop here for now. We will continue with the field expressions for the other modes.